Now let's go a little farther. Angular momentum is the most general definition of angular momentum, and this is just the definition, is r cross p, and which amounts to mass r cross v, since the linear momentum p is mv. But for a rigid body that rotates about an axis, so rigid body just means that all of the particles are stacked together and they move together. For a rigid body about rotating about an axis. Well, I guess I'll put this here. Rotating about an axis, L becomes, how should I do it? L becomes just I times omega. So if you have if you have some kind of an object, here's an object, here's the axis of rotation. And let's say this thing rotates at some omega. As long as you know the moment of inertia, you can calculate and see what's going on here. So this is, this is the big mass, if you will, and this mass rotates at omega about an axis. Then all you have to do is do this stuff where omega is the angular speed in radians per second, and I is the moment of inertia. Moment of inertia. Let's derive this expression. Let's make sure that this does in fact work. But this is something that you are responsible for just as much as you are responsible for this one. If you have a point mass and the mass is moving, and I ask you to calculate the angular momentum of that point mass, then you go to this equation. But if you have a rigid body and the body is rotating about an axis, fixed axis, then you go and use this equation. Or you could start from here and then derive it and end up in this place as well. But that's more work, I think, than what you would want to do. So let's confirm that that is true, and then I'll solve a sample problem. So let's say we do have this rigid body here that is allowed to rotate about this axis. So this is the axis of rotation. And what I want to find is an expression for the, let's just take some mass. Let's say here's a mass m1. And this mass is moving along a circular path here, since this whole object is rotating, right? This whole object is rotating here, and so this mass is also rotating. Now what I want to find is the angular momentum of this mass m1 about the axis. I put here angular momentum about the axis. It would be the mass m1 times the position of the position vector, where this vector points from the axis of rotation to the point mass cross v1. So this would be angular momentum of this particle 1 about the axis. And so now r is right here. R is the distance, the shortest distance from the axis of rotation to where my mass is as this moves around, right? Because I want the angular momentum about the axis, not about a specific point. I don't want the angular momentum of this mass so much about a specific point here or here or here, but about the axis. And so I'm looking for the shortest distance to the axis. Now then, let's take some mass m2. Maybe we'll put this mass m2 here. And I want to calculate angular momentum of mass m2 about the axis as well. And so that will amount to m2 times r2. This is r cross v2. And of course, this is, I have to go back and figure, well, anyways, so here's r2. R2 is going to point like that. Here's my r2. 90 degrees to the axis, 90 degrees to the axis. And then this mass m2 is also moving along a circular path here, because this whole body is moving. And then note that the velocity vector, which is tangent to the path, is going to be at 90 degrees, because that becomes the radius of the circular path here, and then this is tangential, so it's got to be at 90 degrees. This here also becomes, this is the radius of a circular path. Here's the velocity vector, which is tangential to the circle, so here I have 90 degrees. So I'm going to put on the side here that R1 is perpendicular to V1. I put here on the side that R2 is perpendicular to V2. And then I could do, let's just do some random Li. So let's say there's some mass, oh, not that much room here. Well, some mass, some arbitrary mass Mi, it would have radius Ri cross Vi. Maybe, I don't know what I'm going to do. I'm just going to cheat a little. I'm going to call this mass Mi. So this is mass Mi, therefore this is Vi, and that's Ri. That works for me. And then note that I get the same story. That is that's R. Ri is still perpendicular to Vi, some arbitrary, for some arbitrary mass. Now what I want is the total momentum of this, total angular momentum of this whole thing. So I don't want just L1 and L2 or some Li, but I want the total angular momentum about the axis. Now the total angular momentum of the entire mass, big M, about the axis. So what that will amount to is a summation, sum of Li, all of Li's about the axis. And of course, so let's take it a little farther and see where that goes. I have an expression for this Li, so I'm going to replace it with Mi, and here's Ri cross Vi there. And I guess I should keep the vector notation here, and so also here and here and here. Now what I'm going to do though is I want to get the magnitude for this. So I'm going to write L total, the magnitude about the axis. It's going to be summation Mi, and then I want the, well, since Ri is perpendicular to Vi, I'm just going to go run off of this. Since this is perpendicular to that, what I can write is that Ri cross Vi. So here, what that gives me is that this whole thing here becomes, let me move it a little to the right. This whole thing here becomes Ri Vi sine of 90. Sine of 90 is 1. This is 1. Well, doesn't look like 1, but I guess it's 1, which amounts to just Ri times Vi, where I drop the vector notations. It's just the magnitude of R times the magnitude of V. So what I can do is I want the magnitude of L here. So this becomes Mi, and then this just becomes times Ri times Vi, and I'm not putting vector notation, I'm just writing out the magnitudes. But then I can go a little farther. What I can do is I can write that, well, Vi is just Ri times omega I. It's just the old equation where it's tangential speed, and this is the radius, and this is the angular speed. But omega I is always the same for whatever particle I'm considering, whether it's whatever particle, whatever piece of mass I'm considering, they will all have, they will all be covering the same angle in the same amount of time. So what I have here is the same as omega 1, same as omega 2, same as any omega I want it to be. So really, I'm just going to call all of this simply, it's just omega. So what I can write is Vi equals Ri times omega. And remember, omega, that's theta over time, right? And all of the masses cover the same angle in the same segment of time. So the expression for the total angular momentum about an axis then becomes, oh, where am I? There I am. So Mi times Ri times, instead of V, I'm going to have Ri again times omega. And now you should see where I'm going. The total momentum about the axis, I'm just going to put the axis here now only, is the summation sign of Mi Ri squared. Put this in parentheses, times omega. But we recognize this expression as the moment of inertia. And so the angular momentum about an axis of a rigid body is simply I times omega. So from the definition of angular momentum, which is this, you can in fact derive an expression for the angular momentum of a rigid body as it rotates about an axis, and then you end up with this here. Now let's solve a problem. So let's make some room. Maybe I'll slide it this way. It's in the same worksheet, worksheet 2. Problem, I don't remember which problem. Let me go look at it. So it was problem 7, worksheet 2, and problem 7 is what we're looking at. I copied it and pasted it. So a 2 kilogram disk of radius 2 meters is rotating at about its center of mass at 5 radians per second. So let's draw it. Let's draw it like this. Here's the disk. And here's the axis through the center of mass. And this thing is rotating at some omega like this. In fact, omega is given, that's 5 radians per second. And radius r and the mass of this stuff is given. So I'm going to put here big mass is 2 kilograms. And then the radius of the disk is 2 meters. And I'm asked to calculate the angular momentum about the center of mass. Of course, center of mass is right here at the center. So here's just cm, center of mass. And you could start, if you wanted to, really, you could say the angular momentum of the entire mass about an axis, and then you'd have to, if you wanted, you could start from here, r cross p. But why do that if we already have an expression for the total angular momentum about an axis of a rigid body, and that is L equals I omega. It's just a lot easier to go here. And this is a disk, and the moment of inertia for a disk, that's something you know where to look up. It's in your textbook. Forget the page 200 and something. It's half mr squared times omega. And you simply plug in the numbers. So a half times mass was 2. Radius is 2, so 2 squared times 5. And that gives us, so this nicely cancels out, 4 times 5, that's 20. And then the units would be, the units were kilograms times meters squared over seconds. So this is the angular momentum of this disk as it spins about the axis of rotation. And that axis goes to the center of mass. Okay, so now yours are problem numbers. I think you just need to finish the worksheet. Let me check. Yeah, so yours are problems 8 and 9 from this worksheet. Calculate angular momentum for some rigid body. It's pretty easy to do. And all right, so now all of this stuff, we've done all of this to bring us to a certain point, certain specific location. So we have 2 types of momenta. We have the linear momentum. Linear momentum, and that is defined as mv. And then we have the angular momentum. And we have defined that as L equals R cross P. And then for rigid bodies rotating about a fixed axis. So it's kind of very specific, right? This is the most general expression for the angular momentum, but for rigid bodies rotating about a fixed axis, L is I omega. So this is a very particular case. This is a very particular, let me put here, particular case. And this is a general case. Right, that's general case. Okay. So why is this useful? Well, it's useful because this is the first time we're going to get to certain conservation laws. So we have the conservation of linear momentum, and we have the conservation of angular momentum. And whenever we find a conservation law in physics, we get very excited because these things are useful. So what we want to find out is under what conditions momentum is conserved. That is, what we want to see is when do I get dp dt being 0. Because if the rate of change of momentum is 0, then that implies that momentum is constant. And if momentum is constant, that means that momentum is conserved. what I get is that some initial momentum equals final momentum, right? Momentum at any time stays the same. That's a conservation of linear momentum, and that's when we find that this is very useful. Likewise, we can do something something very similar with angular momentum, and with the angular momentum, we would do dl dt. We want to find out when is this 0, because when that thing is 0, then we get that the angular momentum is constant, and that means that Li equals Lf, and we have another conservation law. So we get conservation laws. And so let's see if we can figure out the conditions when, under what conditions are the two momenta conserved. So dp dt would be ddt of mv, and that of course gives me m dv dt, and that of course gives me ma, and that of course gives me f net. So what I could write, we can take it a little farther, but what I can write is that dp dt equals f net. In other words, when the net force on an object is 0, then the momentum is conserved. There's more that I will have to say about this, because we will eventually do is we're going to say that the net force on an object is the sum of all of the external and internal forces, sum of all of the external and sum of all of the internal forces. But the sum of all of the internal forces will amount to a big 0. Right? The forces within the object or the forces within a system, they cancel out because they all exist in pairs. So opposite and equal and opposite reaction forces, that goes away. And so effectively then F net becomes just F external, the sum of all of the external forces. And so so typically the way it is stated is that dp dt is equal to force external, or the sum of all of the external forces. I'm just going to put external force, but it's really the sum of all of the external forces. In other words, if F net, or I'm going to put in parentheses just F external, is 0, then I get conservation of linear momentum. Pf equals pi, and this is the statement of the law of the conservation of linear momentum. In a similar way, we can do something with this here, angular momentum. So what we'll do here is dl dt equals d dt of r cross p, or I'm going to use, to speed up the process, instead of L, I'm going to write m, well, not instead of L, but like this. Here's another way to write r cross v. Right, so I can do that. M is a constant, so m just comes out. And yeah, why not? Let's just show you this part too. So m, and then I'm gonna get, well, you have to kind of distribute this thing. So you're going to end up with dr dt cross v, and then plus r cross dv dt. You have to distribute this thing. And let's take it a little farther. So what I have is dl dt equals m times, well, dr dt, that's v. So I'm going to end up here with v cross v plus r cross, and then dv dt, that's a. So I'm going to end up here with a. I'm going to close this. Now v cross v, any vector crossed with itself gives you 0. I mean, if for no other reason, the angle between the two is 0. So the magnitude of this would be v times the sine of 0, which gives you 0. So that just goes away, and now you end up with r cross a, or dl dt is equal to, I'll take a bit of a shortcut, and I'm going to do this, r cross ma. But what's ma? As I take this is just a constant. I can put the constant anywhere I want to. I'm going to put it in front of a. It gives me ma. But ma is just f net. And so here what I have is dl. Let's go this way. Whatever. So let's go this way. dl dt equals R cross F net. But what's R cross F? R cross F, that's the definition of torque in a vector form, right? The way we did it was that torque is RF sine theta, but that was because we were interested in the magnitude. It was just easier to go straight for that. Though it's really R cross F. And so since this is F net that I have there, this is the net torque. And so the L dt is equal to the net torque. In other words, I can make the statement of the conservation of angular momentum. Look at that, ran out of. So we're just right, with just enough room. So if the net torque, and this can be also argued that this is just the external torque. If the net torque is 0, then what I get is that the rate of change of the angular momentum is 0, and that of course gives me Li equals Lf, or that the angular momentum is conserved, and so you get conservation of angular momentum here. All right, so I gave you the 2 conservation laws. Can I squeeze them both in one page? No, I cannot, but I can almost do that. We will solve problems with both of these things, but for the moment I'm just giving you the result, the derivations. So you should finish this worksheet, do this stuff. Be familiar with the statement of the conservation of linear and angular momentum, but we haven't done any problems with them, with these equations yet, with the conservation laws yet. So just don't worry about it yet. Once we start solving the problems, then you will have to worry about it. But then once we start solving the problems, you will also understand these conservation laws a bit better. All right, so anyways, I think I'm going to stop here. You have some problems to do. You should do these problems.